All of you have most likely heard of the coronary artery disease, where there's a buildup of plaque blocking the arteries, causing insufficient supply of blood to the tissues. This condition of lacking blood flow is called ischemia. Severe ischemic disorders and injuries are usually treated by surgery, which, though effective most of the time, is kind of hard to do and very expensive. Right now, there's a growing interest and popularity in cell therapy, and the Ohio State Center for Regenerative Medicine and Cell-Based Therapies, headed by Chandan Sen, in collaboration with its College of Engineering, developed a new technology called tissue nanotransfection, where with the use of a nanochip device that they also developed, researchers can produce any type of cell that they need for the treatment of disorders such as ischemia, from skin cells through a simple and non-invasive method. Now in tissue nanotransfection, plasmids encoding reprogramming factors will be introduced into the skin cells via nanochannel electroporation. This is done by applying a pulsed electric field across two electrodes, the anode inserted intradermally and the cathode in contact with the plasmid solution, to temporarily open up pores in the cell membrane. The plasmids are then electrophoretically driven across the nanochannels in the nanochip device and through the temporary pores, thus delivering the reprogramming factors that will trigger the conversion of skin cells to the desired cell type. Then, to check if TNT can actually help repair tissues, the researchers from Ohio State University tested it on the ischemic limbs of mice, planning to produce endothelial cells that will help in the formation of new blood vessels. As seen in the laser speckle imaging, there was not much observed blood flow on the ischemic limbs at day 0, but days later, the blood flow was regenerated on the injured area of the mouse treated with EFF-TNT. This is also shown in the perfusion ratio plot, where the EFF-TNT treated limb had increasing perfusion since day 7. Macroscopically, it was observed that the control had more pronounced signs of tissue necrosis than the EFF-TNT treated one. Overall, this showed that EFF-TNT was able to rescue whole limbs from necrotizing ischemia. At present, there are other transfection methods that also employ the technique of electroporation, such as BEP and MEP. As described earlier, electroporation involves the use of an electrical pulse which disturbs the phospholipid bilayer of the cell membrane, forming temporary pores. The electric potential across the membrane lets charged molecules like DNA move across the pores in a way similar to electrophoresis. Currently, BEP is the most common and is widely used for its simplicity and operational flexibility, but it has disadvantages like serious cell damage and low transfection efficiency. MEP, on the other hand, has better cell viability and efficiency than BEP. However, both methods rely heavily on the diffusion after the electrical pulsing for their transfection agent uptake, demonstrating no precise dosage control of the said agents. Meanwhile, tissue nanotransfection with its nanochannel electroporation exhibits negligible cell damage and negligible agent diffusion after poration. Because of its nano-sized channels, the electric field becomes highly localized and focused, inducing a strong electrophoresis that quote-unquote injects the agents at high velocity into the cell cytoplasm, simultaneously with the electrical pulse. This results in TNT having a rapid, more focused, and ample reprogramming factor delivery. Another advantage of TNT includes having a simple and non-invasive or topical implementation method. Also, the approach is non-viral, thus avoiding adverse side effects like inflammatory response. The reprogramming method can also be done in vivo, which offers advantages such as readily available cell sources, no required ex vivo preprocessing steps, and resolving conditions locally or on-site. Additionally, the cells produced are autologous, meaning they are from the same individual, which risks the need of immunosuppression. Under the Ohio State Innovation Foundation, the researchers applied for patents for both the reprogramming method of skin cells to endothelial cells and the design of the nanochip device for nanotransfection. These patents, as shown on the right, were filed in 2017 and were just recently published last June 2018. On the left, an earlier patent, which was published in 2014, was applied by the same university where it describes the method for the high-precision transfection of cells by nanoelectroporation. tissue nanotransfection provides room for many improvements and possible applications. As mentioned earlier, TNT can be used to produce any desired cell type, not just endothelial cells, given the right set of reprogramming factors. This opens the possibility of treating other diseases like Alzheimer's and Parkinson's disease. And it's not just skin cells that can be transformed. Other cell types can be used as the initial source. Depending on the circumstances, it will help make future treatments using TNT simpler by possibly removing the step of harvesting cells from the skin. And lastly, since TNT makes use of cellular reprogramming, there's also a chance that possibilities brought by cellular reprogramming could also be done in TNT. Regeneration was shown to be possible in the study, so maybe something like reverse aging is achievable. Future work still needs to be done in this research, but nevertheless, this technology opens an avenue in regenerative medicine.